So hopefully at the beginning or the first time that we have class every week, we're going to go through and deal with a parent function that you all will need to know, not only for this, but as you work your way through mathematics. So to start this, put your name at the top. This one will be week 1. Let's do, to start off, do the identity function, y is equal to x. Now, in terms of what the graph of that looks like, you can make a table of values if you need to. We like to center at 0. 10, so maybe make this 0. We'll do -1, -2, -3, and -4, and we can bounce up and go 1, 2, 3, 4, 5. This would mean that my output is -4, -3, -2, -1, 0. Whatever the input is, that's going to be the same as what your output is. So if I were to graph this out, you end up getting, go through and graph out all those points. And we'll answer as many of the questions as we can. We're going to encounter some stuff that we haven't quite done yet. If you go through and graph out the identity function, that's what it would look like. Do it maybe red, bigger. So that's what the line y is equal to x would look like. Thinking in terms of domain and range, we need to ask ourselves what values will give me an output. So looking at what's there, Alyssa D, what would the domain on this be? There you go. -infinity over to +infinity. How about the range on this? What values am I going to be getting for the range? Jensen, what do you say? Yeah, every value on this is used. So there's a couple questions that we're going to get to as we work our way through. How about, let's do this first. Increasing. Now, again, you haven't done this yet, but it's not exactly rocket science. As we work our way from left to right, over what interval is it increasing? And there's two different schools of thought or two different definitions. But one of them, the one that we're going to use, is as I go from left to right, it's increasing if the next point that I encounter is higher up than the one that I'm currently at. So looking at this, my increasing interval, does anybody want to take a guess as to what the increasing interval would be? Based off of that definition. Think about if you're running along this line. It's increasing when your next step is a 1 higher than you are. What do you want to say? No? Tyler? Yeah, it's always increasing. As I move from the left to the right, it's always going up. So, when is it decreasing? Hands up, please, if you can answer that. It's increasing from negative infinity to positive infinity. Nope. Remember, it's only going, you can only run this way. Never. And when is it constant or flat? That would be never as well. Now, when is the function greater than 0? So take a look at your graph. The function is the output or y values. When are the y values going to be greater than 0? Over what interval are the y values going to be greater than 0? We've got one person that can tell me. Take a look at what's there. What do you want to say, please? Two? Close. She said from 1 to infinity with a bracket. Now say your answer is even a subset of a bigger answer. Yeah? Everything after 0 to the right, not inclusive of the 0. Now when is the function or the y value going to be less than 0? Hands up, please, if you can answer that. 3 of you, 4. How about when does the function equal 0? Yeah, just at a 0. So you could say at x is equal to 0 or give it as an interval, which is the number 0. When are the zeros of this? Well, remember we discussed previously to find your x-intercept, which is the same thing, you would set your y to be equal to 0. So my function originally is y is equal to x. I make that replacement. My intercept then is the point 0, 0. Now, how about when we're talking about maximums? Thinking about this graph, does this graph have a maximum?
No.
No. It's unbounded above, meaning it rises forever. What about the minimums on this graph? Hands up, please, if you can answer that. What's the minimum? Yeah. Doesn't have a minimum either. It's unbounded below. Now, we need to figure out, we haven't done inverses yet, so in future ones we'll come back to it. For this one, it really doesn't matter. Is the function odd, even, or neither? Well, I'll say this. You need to plug in, let's say this too. We'll scrap this piece of it right now. We'll come back to it maybe next time we do function week. I'm pretty sure we'll hit that. We can do this down here, though, these last two. And actually, we can answer this one. Who remembers what it means if a function is onto? We talked about that last class when we were going a little bit above and beyond what a function was. Who remembers what it means if a function is onto? We've got 2 people, 3 of you, 4. You've already listed it out in your notes. What do you want to say?
It's a function that continues without any breaks.
No, that would be a continuous function. Tyler? I'm sorry, every single output what? Yeah. What it is it's a relationship in which every single output that's available is used. So, in this case, on the Cartesian plane, the outputs are the y values. Is every y value used? Yes or no? As I go down to negative infinity, they're all used. As I go up. So I would say that this is onto. So we say every output is used. How about if we're asking whether or not it's one-to-one? Well, in order to figure out whether it's one-to-one, you all love this Lazy Larry definition. We'll go into what it is in a little bit. A function, it passes the vertical line test. That's the lazy definition. A one-to-one function will pass the vertical line test and the horizontal line test. Is this function one-to-one? Does it pass the vertical line test? It absolutely does. Every time we graph, or every vertical line we draw touches at most once. If it passes that, to see if it's one-to-one, then we would go through and try the other end, which is seeing is every, if I draw a horizontal line, will that touch twice? And the answer is no. So this would be, we'd say yes. I guess this for Algebra 2 is an adequate test, even though it works off of properties. Are there any asymptotes, which are lines that it gets infinitely close to and doesn't touch? We could say no. These don't apply. These are for trig graphs when we do them. As x goes out to positive infinity, what is the function value going to? Think about that. As I ride this graph out forever to the right-hand side, what are the output values going to go to? Who can give me a guess as to what they think what would happen? If I went out to the right-hand side forever, the f of x is the y values, what do we think that that's going to go to? We've got 2 people, 3. Should be better than that. What do you want to say? What kind of infinity? A positive one or a negative one? Terrific. So as I go out to the right forever, my function values are unbounded. It goes to positive infinity. How about as I go to the left? Let's see if we can get 8 of you that can tell me that. We've got 1, 2, 3 so far. 5. What do you want to say, please? Terrific. Now, take those, please set them to the side. You're going to want to hang on to them. Because as we go throughout the year, you're going to have one, hopefully every week. We need to get through about 20 to 25 of them. You need to know what your parent graphs are in order for you to be good with transformations. So hang on to it, that's the easiest one. Now, have out on your desk your note package, please. Open to where we left off last time. We'll get to homework at the end if we have time. But we need to make sure that we get through as much of this as we can today. What we're talking about today is this. We're talking about what the inverse of a function is. Where did we leave off?
We left off at 9.
All right, page 9. Or sorry. No. Yeah, go over please to page 18 at the top. You're going to want to get this down someplace in the margin. This is what it means for a function to have an inverse. And then we'll walk you through what it is. This is a huge topic in Algebra 2. It accounts for about 8% of the Regents exam, or at least it used to. It may account for more or less now, but it's a big topic. You need to know about inverses. There's 3 ways to view it. If you're given a collection of points, you simply transpose the x and y coordinates to find the inverse. So someplace on there, we ask that you freehand write this down. If you're asking to take the inverse of a relation, you would simply go through and take all of the inputs and outputs and switch them. Your domain of the original will be the range on the inverse. The range of the original will be the domain of the inverse. You transpose or switch the x and y coordinates, so the point AB becomes the point BA. If you're given a graph, the inverse will be a reflection over the line y equals x. That diagonal that we just did for our function of the week, that's going to be what our inverse is going to be reflected over, that diagonal. And again, you should know that the line y equals x is simply the diagonal going from the bottom left to the top right. And the last thing has to deal with an equation. To figure out the inverse of an equation, you switch the x and y and solve for y. Now here's why we talked about a one-to-one function. And this is important, especially as you go on to calculus and to pre-calc, because we need to make sure our function rules are followed. If the original function is one-to-one, meaning it passes the vertical and horizontal line test, then the inverse will be a function, and I know that without finding the inverse. So what that means is, if I look at the graph, and it passes the vertical line test and the horizontal line test, we know that the inverse will also be a function. If the original does not pass the vertical line test and the horizontal line test, the inverse will not be a function. Are you stealing what is that? All right, so make sure, please, that you have that down. We're going to reference it throughout the year. You need to know these things. I put a big old star on. If you want, I think you can go and get this tattooed on yourself for about $25 at White Tiger Tattoo in the Village. It's an academic special. I think that if you get a math formula tattoo, the only problem is you still can't use it on the test. But I'll let you use it on any test. All right, so let's take a look. Now, you already, whether you know it or not, have a great deal of understanding about what an inverse is. Inverse operations are ones that undo each other. So adding is its inverse operation will be subtraction, multiplication, inverse operation is division, squaring something, the inverse operation is the square root, and so on. What you need to know is inverses are denoted by that notation. If a function f is a relation, then the inverse is f prime, or sorry, f inverse of x, f inverse of x. And if you take that composition, if I take the inverse and plug it into the original in the input spot, I'm going to be left with the original x, be left with just an x at the end. That's something that doesn't come up that much, but you do need to know that if I were to take the composition, take a function, plug its inverse in the input, and simplify it out or do the operations, if they are inverses, it leaves me just with an x. So here's two examples. If we go through and do this out, the inverse undoes the function. So if the function, you start off with a foot, you put your sock on as the function, taking the sock off is going to be the inverse function to get you the original. Now, if I were to go through and take to start off, here's my function, I add 2 to start, the inverse would require me to go through and subtract 2. Now, we're going to deal with some of these that are a little bit more complicated than others. Let's start off. Yeah. Well, if we start off, if I take, based on this relation, if I start off with a 1 and plug a 1 in, my output would be a 2. If I start off with my function and take the 2, I would get a 7 as an output, and so on. That same thing, then, the inverse is going to contain that going in the other direction. So your inputs become your outputs, and your outputs become your inputs. If this is my original function, if that's what we're defining it as, hands up, please, if you can tell me one coordinate that would be in the inverse of that f of x. We've got 1, 2 of us, 3. Tyler, what's one point that's going to be on the inverse? 2, 1 is going to be on the inverse. What's another point? Johannes, what would you have on the inverse? 7, 2. And the last one, Trevor P., what's the last one going to have on it?
-1, 3.
What's that?
-1, 3.
There we go. So if f of x is a set of ordered pairs, we would go through and switch the x and y. Therefore, the domain of the original is going to be the range on the inverse, and the range of the original is going to be the domain on the inverse. So the x's of the original are the y's, or the inputs of the original are the outputs on the inverse, and so on. You just switch the x and y and solve. Questions on that? Yes.
Sorry, what was the thing that you started accidentally right over?
What do you mean?
I didn't write all of it.
From back over here?
Yeah, the original is one, the inverse will be a function. Does that just mean if you invert, is the inverse function going to be the same as the original?
No. We'll see more examples of it now.
Wait, I need to...
We'll put it up again. Now, it says, what if the relation is given as an equation? Now, looking at what's here, let's track what's getting done to the input. So in the original, the first thing getting done to the input is I take the input and multiply it by 2. Then to that value, I go through and subtract a 5. So as we see, if I plug an x into my function, I multiply by 2 and then go through and subtract by 5. Now the inverse is going to have us do things in the opposite order. And it's going to go the other direction. So the first thing that I would go through and do is add a 5, because that was the last thing that I did before. And what else am I going to have to do to it? Hands up, please, if you can tell me. What's the other piece? Go ahead. Divide both sides, or divide, excuse me, the answer that I had by 2, and that's right. So what I do, I need to undo. And the inverse then would give us, as an expression, take my input, I added 5, and then divided that answer by 2. So let's test and see what we get. To start this off, if I have an 8 and I plug it into my f function, hands up please if you can tell me what numeric value I would get.
Oh, I love it.
Hit the S. What do you get when you plug an 8 into the original function?
11.
Now, let's go through and plug in 11 into our inverse. Hands up, please, when you can tell me what you get when you plug in 11 in the inverse. 3 of us, 4.
Oh.
Sarah L., what do you say? There you go. Did the inverse undo the function? Absolutely. Now, your first step in doing these, we listed it out before. You tell me, what did we list out if we're given an equation? Taylor, what was the first step in order to find out what your inverse was? We're given an equation. What would your first step be to find the inverse?
Reverse the steps.
No? Should have listed it out when we did it before. You can tell me what our first step will be. If you've got an equation, you got to find the inverse. 2 people? 3? What did we write out?
Switch the x and y in
Yep.
the original equation.
Okay, so let's do that to start. We're going to switch the x and the y in our original equation. So that's our original. Allison L., what is this going to look like when I switch the x and the y?
X equals 2y.
All right, so we did that. Eli, what would the second step be? What was the second step that you listed out from before? We switched the x and y. What do we do next? We should have listed it out on the very first page. Who can tell me, please, what this is supposed to be? Yes.
Solve the equation.
Switch the x and the y, and then I'm going to go through and solve this equation out for y. So when I do that, I need to get the y by itself. What would your first step be? Emma K., what would that first step be to solve for y? So I've got x minus 7 is equal to 2y cubed. What would we do next from here? Jonathan?
Divide by 2.
Divide both sides by 2. So I've got x minus 7 over 2 is going to be equal to y cubed. What's the next thing that we would go through and do from here? Jason?
You would have to get the cube root, so put that under radicals, so it's a radicand, and then equal to.
So the last thing that we're going to do is state what that is. And now I'll go through and say, you could say y inverse, because it doesn't use function notation. So y inverse is going to be equal to the cube root of x minus 7 all over 2. Now, go into your calculators, please. Everybody right now, go into your calculators, please. Now, go in right now and go into a new document. Again, you shouldn't be working in Scratchpad, because if you are, I can do this right now. Where was that? There we go. Now, done. Okay, go in, and we're going to need to go through hit menu. We're going to give a graph, so add graphs, which is 2. Now, we're going to graph out 3 things. The first thing I want you to do is plug in the original y equals that you were given. So go in, please, and plug in the original y equals that you were given, which was what? Y equals 2x cubed plus 7. Did I remember that right? Okay. So that's what the original is. Now, when we graph out the inverse is going to be the reflection of this graph over the diagonal line y equals x. So let's go in now and graph out and hit is it Control T?
No, that's a table.
Oh, that gives you a table. What gets it? Control G? Oh, okay. Hit Tab, I guess, and it'll go through and do that. In any case, go in now and put in y equals x and F2.
Oh, just y equals x.
Yep. Now, our answer is going to be what I get when I reflect this blue line over the red one. So you should know about what it's going to look like. If I were going to take this and reflect it over, this would be something maybe over in here. right? And this piece here would get reflected over here. Now go in, please, and add another graph onto this same set of axes and let it be the cube root. So the cube root or third root of, and you do control division, and it's x, careful, delete what's in there, because control division to make sure you get everything up in the numerator. And was it x minus 7 over 2? Okay. And we're going to take the cube root of that and hit enter. Now notice the original function is 1 to 1, so the inverse will also be a function. Notice that if I take this blue graph, reflect it over the red, I get the black one. That's what an inverse does. It takes the original, reflects, and all of the points on the original, if you transpose the coordinates, are going to be on the inverse. So let's say this right here contains a point like -1, 5, then the inverse would contain the point 5, -1. Notice that the domain of the original is the range of the inverse and so on. And that's because this original is 1 to 1. Who can think of a graph, a type of graph that we use all the time, that would be a function but is not 1 to 1? Hands up, please, if you can think of a type of graph that we use quite frequently that would have be a function but is not 1 to 1. Yeah, your quadratic, that's going to give you a parabola, which would pass the vertical line test but fail the horizontal line test. So the inverse itself won't be a function. We'll go over how to restrict our domains later. Well, what if the function is given by a graph? We covered that as well. We're going to take and reflect over the line y equals x. So if that's our original function, you're going to ever so lightly graph out your diagonal here, which is the line y equals x. Hands up, please, if you can tell me one coordinate that's going to be on the inverse of this f of x. Take a look at the graph. You tell me one ordered pair that would be on the inverse. Would you like to say? All right. You said 1, -1? No. Because what's this coordinate over here going to be? This would be the point -1, 0. So what's the inverse going to have? Go over 0, go down -1. Yeah. Who can give me another point that would be on this inverse? 2 of you, 3. Noah, what do you want to say?
2, 0.
2, 0. That works. There's one more that I can easily get. Yeah. 4, 1. So go over 4, up 1. Now, let's label it, please, as f inverse of x. Is the original f of x a function? Alexa, yes or no? Furthermore, well, is the inverse a function? Let's ask that. Maddie? Yes. Is there a way that I could have answered out this question without actually finding out what the inverse is? You knew that before you did it. Questions on that? Every relation has an inverse. Now, it's possible, by the way, for you to take the inverse of something that's not a function. It just means then the inverse won't be a function. Every relation has an inverse, therefore every function has an inverse. Not every inverse is also a function. So, as we're going through, we discussed this. You all were very astute in determining that if I go through and graph out a parabola, something that looks like this, and then I go through and I take its inverse, which would look something like that. Is the red a function? Yes or no? No. Doesn't mean you can't get it, but the problem is that all of our algebra rules that apply to functions stop applying and stop working. So what we have to do is we have to come up with a solution. Instead of sitting there and saying, we're done, this doesn't exist, and wash our hands of it, we go through and say, well, is there something I can do to the blue graph that would make it so its inverse would be a function? Think about that for a minute. What can I do to the blue graph so that when I take its inverse, that would be a function? We've got 1, 2 of you. Be a problem solver, we got 3. What could you do to the blue graph that will result in the inverse being a function?
If you rotate it to where the red is, and then make the inverse of the back.
The problem then is the original. If you're talking about making the red the original, that wouldn't be a function. What other ideas do we have? No? See, I look at it and I get kind of,
Basically, on the hypothesis that if we do the reflection on the earth.
so you have sort of a parabola on an axis? Right? I view it this way, because that would be a function.
So like, you know how like there's the square root functions?
Mhm.
So just get rid of the negative part of the square root, so it just only shows the square root.
Now, what he's getting at, or I think you're getting at, is this. Here's the original. As it stands right now, is the original a function? Is the blue
Yeah.
graph a function? Absolutely. Is it 1-to-1? No. How about we just make it be 1-to-1? Where's the lowest point on this graph going to be? Well, right about here. This is called restricting the domain, so I can go through and say, all right, I'm going to look at the positive half of this graph. So if I look at the positive half of the graph, say I'm only going to use x is greater than 0. Is this the graph of the inverse then?
Yeah.
Mm-mm.
Or no.
Hands up, please, if you can tell me what the graph of the inverse will look like then. Take that blue graph, we restricted down the domain. What's the graph of the inverse going to look like? Because you're partially right. You've got to work with sort of thinking of like a surgeon. Yeah. So you're saying you're viewing this in 2 halves right here? Which half is the one that's the inverse of this, or this reflecting? Is it this top half or the bottom half? What's that? Mm-mm. It'll be the top half. Did I just now, by restricting the domain of the original, did I make that be 1-to-1? Is the inverse a function? Sure. Now, by the way, can we do it? And there's always some people who are obtuse when they do this and like to be difficult. And they go, fine. I see this, and when I do it, I like to stay with the negative half. So fine, be difficult. But now you tell me, how is the inverse going to change? Hands up, please, if you can tell me what the inverse of that blue graph is going to look like. We've got 5 people. Oh, better. We can do better. We can do better. What do you want to say? Which piece is going to be the inverse? Which would be the inverse of this? Would be the top half or bottom half? No? Because see how if I reflect this over here, this would sort of go and bounce down over here. So when we did this, this piece here would be our inverse. So if you restrict the domain, that's fine. You're going to get an answer, or an inverse, that is a function. Let's take a look and remember that the domain of the original is the range of the inverse and so on. So let's start off with this. And we're going to begin with 3x minus 2. Find the inverse. Is the inverse a function? Well, go through right now, please. Find the inverse on your own, quickly. That's how quickly you all should be able to go through and do that last piece. Questions on that? Think about the original. If I were to graph this out, Jess, what would it look like? If I were to graph out the original. Yeah, what shape would the graph be? Yeah, it's linear, it's a line. You could go in and plug this in, you graph the original, graph y equals x, and see that they cross. Now let's go through and look at a different one. And it's going to be find the inverse. Is the inverse going to be a function? Now right away I noticed something awkward about this. What shape is the original function going to be? Peter? What shape is that graph going to be? Yeah, it's a parabola. Is a parabola one-to-one? No. So what do we know about its inverse? Will the inverse of this be a function? No. So here's what we're going to do. Go through right now. Well, let's see if we restrict the domain in this one or the next. Thinking about what's here. Go into your calculators, please, right now. Clear out what's in there. And let's graph out the original, please, in this case. So go in right now. We're going to give a new graph. And in that new graph, we're going to plug in, what did we start this with? Go in and put the quantity of x minus 7 being squared. Now, I don't know. There we go. So there's our graph. When I go through and reflect this over the line y equals x, so actually go in right now and do y equals x, your inverse is going to be a sideways parabola that goes through the point 0, 7. We don't have, or our inverse then would not be a function. So what we're going to do instead is this. I'm going to say that's fine. Now, there's a big decision here. Which half do you want to look at? Do you want to break this down so I'm looking at the left half or the right half? Okay. Now, looking at what's there, we're going to say, we're going to force this to be our inverse if the x is greater than or equal to 7, because that's looking at the positive half of it in terms of what the graph is. That means we're looking at this piece here. Is this right half of the parabola, is that one-to-one? Yeah, it's the whole parabola that's not. So what we're going to do is, I'll start off and say, this is going to be y equals the quantity x minus 7 being squared. I would switch the x and the y, so it will be x is equal to the quantity y minus 7 being squared. Now, I need to go through and determine what my inverse is going to be. So, what do I have to do to get the y by itself? I'm going to ask, what do you say? We're going to square root both sides. So this would leave me with the square root of x is equal to a y minus 7. And from here, Michael, what would you do to get your inverse? So this would be our y inverse. So to finish it up, in terms of function notation, this is what we would be left with. But we do have to go through and place some constraints on this. You need to make sure that you indicate, well, and we did it. We did our domain restriction in the beginning up here, that the x would have to be greater than or equal to 7. Let's go in now and do this. Go in, please, and you get out of 25, is that right? Okay, let's do this. Go into your calculators, please, and graph out on the same side of the axis. Let's do the square root of x plus 7. And we're actually going to need to modify our window so you can see that graph because it's going to be too high up. So go into menu. We're going to go to graph, which is, I think 3 is where you find it. No, go back. Oh, window, sorry, window 4. We're going to go to window settings. Now, I'll tell you this. Sometimes people go through and they constantly do this, and I like to call it zoom stupid, because they train you like dogs. You just zoom out, zoom out, zoom out. Put things in terms of perspective. The graph isn't going into the 3rd quadrant or the 4th quadrant. We need to go up a little bit. Our X-min and our X-max are terrific. So we can skip that part. How about our Y-min? Even that's, we'll leave it as it is. But we need to see up a little bit higher. So change our Y max to maybe be 20 instead. Or something, you make it 25. Whatever. You pick. Go down and we'll graph that. Now, looking at this graph, see how this piece here went up? If I reflect it over, it's going to go like this. And the two are going to meet at an ordered pair over here. Our scale is just a little bit off because we've got 30 going this way and 25 or 21 the other way. But in any case, you can see that those are reflections of each other. And you wouldn't be able to input the negative x's. That's a domain issue. Let's try to get one more. Bounce over, please. For the inverse to be a function, the function also must be 1-to-1. We've already said that. A function is 1-to-1. If every y value is only used once, the y values that are arrived at are unique. So in terms of what a function is, a 1-to-1 function, every y value that it gets has to be unique. So if I plug in a 7, it gets mapped to a 10. No other input is going to be giving me out a 10. So looking at what's there, is the original 1-to-1? Take a look, please, at 5A. Is the original 1-to-1? Haley, what do you say? Okay. So is the inverse going to be a function, yes or no? And Haley, what about B? Is that g of x, when you graph that out, is that a 1-to-1 function? What do you say? No. So is the inverse of this going to be a function? Now, let's go over and we're going to see maybe when we could have some issues. Take a look at 6. To do this, here's our function. And this is going to bring up with it some domain issues, but it's domain issues of the original. Looking at what's there, how would I go about determining, well, how would I go about determining what the inverse of this is? Chloe, what would your first step be? Okay, so I'd write it out first in y equals form, and then I'm going to switch them. So what would you go through and write out? Terrific. Now, what would your next step be from there? Colleen, B, what do you say? No? Not yet. You've got to get your y alone first. Subtract the 3. So I've got x minus 3 is equal to the square root of y. Now what would you do to get rid of that square root? No? Square it, yeah. So let's go forward from here. I'm going to square both sides. So when we do this, I get y is equal to the quantity of x minus 3 being squared. Well, I guess y inverse if that's how you want to view it. Or f inverse. There's one problem on this. We're going to have some form of domain issue. And when we do it out, the problem that we have is, remember when you go into your calculators, please, bounce over, please, graph out what the original is in this, and then do zoom standard. So go in right now, please, graph out what your original is. Oh, get rid of, sorry, this is going to throw everything on one. Delete the other stuff that's in there. Yeah, just start fresh. And then graph y equals x. Now our inverse, when we graph it out, so go in and plug in the inverse gives you too much. The quantity of x minus 3 being squared. The inverse gives you too much. So which piece of this black graph is the inverse of the blue one? Hands up, please, if you can tell me. Is it to the left of the 3 or to the right of the 3? To the right. So that means, are the x's over here, are they bigger than 3 or less than 3? I'd say bigger. So I go through and say, this is my inverse, so long as the x is greater than or equal to 3. Why do we need to put that restriction on it? Because the original function is 1 to 1. Our inverse doesn't match that. You only need half of the parabola. Now let's give this. Look at the original. What is the domain of the original? Look at the original. What would its domain be? You can either look at the graph or look at the expression. What would the domain, Jack, what would your domain be of the original function? Careful. Where does it start at? What x value? Does this 0 out to? Good. Do you include the 0? What is the range of this going to be? Courtney H., what do you say? Bracket or parentheses at the 3? Now, knowing that, let's answer this without looking at the graph. Hands up, please, if you can tell me what the domain of the inverse is going to be. Without looking at the graph, what's the domain of the inverse going to be? The 3 of us. What do you want to say? No? What's the range on the inverse going to be? 2 of you. Go ahead.
0.
How did you get that? There you go. The domain of the inverse is the range of the original and vice versa. Now, so what we're going to do is this. Before you go today, we're about halfway through the unit, maybe a little bit more. We're getting close to things starting to wrap up. So, your homework, there's really only one question where you may struggle, and that's number 4. I think there's 6 on here. I'm going to ask, please, for homework. This will collect from you not tomorrow, but the next class afterwards. So you've got 2 classes to get this done, and that's done in addition to the homework that you have. Can I see that?
Are we working all the way to the end?
Yep.
Okay. I'm going to put that in my phone.
Take a look at number 4. That gives you out what your homework is. You look at 4 and you've been doing it, just follow along. That's where your homework will be. Pick one of those up, and I'll tell you this. I'll even post the answers to that self-check questions, those self-check questions, excuse me, I'll post the answers to them in Google Classroom tonight. So you go through and have them to work towards. The only one that'll be difficult is number 4. It asks what a discrete function is. I'll say this. If you get stuck, type it in Google and say, what is a discrete function? And then filter through the results so you find the one that would work. But for your homework is day 4 stuff and the ones that are over there. Yes?
What about today's homework? Are you collecting it?
Nope. Probably collect tomorrow's. Grab one over on the side, please. Have a wonderful rest of your day.